So it's just a straight line, and the velocity never changes. That is how a particle moves in configuration space if you don't have any sort of interaction. And in the phase space, the velocity vector, the momentum doesn't change. The momentum is constant. So you stay at a constant momentum. You just fixed at that momentum. So in the six-dimensional space, the momentum p of t, px of t, is equal to px0, py of t is equal to py0, and pz of t is equal to pz0. These are the momenta that you have when you started. For a single particle with no forces acting on it, this is what the evolution of the system over time looks like. Now, you may note that momentum in a particular direction, momentum in the x direction, as a function of time, is equal to mass, the mass of the particle, times the velocity in the x direction. But what is the velocity in the x direction? The velocity in the x direction is the instantaneous rate of change of the x direction with respect to time. That is to say, the velocity is just equal to the time derivative of the position. So to get back the state of spaces, to get back how the object is moving through the state space, if you already know these, then all you have to do is differentiate these functions with respect to time and then multiply them by mass. However, that is not always easy, and sometimes starting with these can be simpler. But that is for particles that are experiencing no interaction. Newton's second law is F net is equal to mass times acceleration. What this tells you, this is your actual law of evolution for interesting cases. What this tells you is, say you know that you have some force in the x direction, but then you also have another force, F prime, in the x direction. In general, when you add all of the forces on a particle, and this second law here can almost be seen as the definition of a force. You'll have different force laws in classical physics, and what those will tell you is what this is equal to given a particular setup. And then this will give you, in general, an equation to solve. It'll be a differential equation to solve, and when you solve it, you will get what the position is as a function of time. Now, when you add up all the forces that are acting on a particle, so you take into account all the different force laws that you have, and you add them up, so you add up all the forces in the x direction, and then you add up all the forces in the y direction, and you add up all the forces in the z direction, then you will get the mass of the particle times its acceleration in that direction. So, we added up all the forces in the x direction. We get some amount F sub x. That is, when we added up all the different force laws, say there was an electromagnetic force, and there was a gravitational force, and several other forces, say a frictional force, and a contact force, all acting at once in the x direction for a particle. We added up all of those values, and we came up with F sub x. Then we know that that is equal to the mass of this particle times its acceleration in the x direction. Now, you might say, what is acceleration? Acceleration is the quantity which tells you how velocity changes with respect to time. Velocity changes with respect to time. That's what a force does. It causes velocity to change over time. So, acceleration tells you how velocity changes with time. Therefore, the acceleration is the time derivative of velocity. So, if you add up all the different force law contributions on an object in a particular direction, that will tell you the mass times the derivative of the velocity in that direction. Notice that you have to take into account the direction. And notice that you only add up the x-directional parts of the force to get the force in the x direction. You add up the y-directional parts of the force to get the force in the y direction, and the z-directional parts of the force to get the force in the z direction. There's a reason for that. The reason for that is because velocity and force and acceleration are all vectors. And as I said, I would get to vectors later. When we do the simplest systems, we're going to start with systems in one dimension, so we won't have to take into account the vector nature of these things until later. Now, Newton's third law, this third law is the one which guarantees that momentum is conserved. It says that if you have two particles, the force of particle 1 on 2 is going to be equal to the force of particle 2 on 1 with a minus sign. That is to say that if you have particle number 1, it acts on particle number 2 with a force. Particle number 2 acts on particle number 1 with the same force, but in an opposite direction. This does not give you any additional dynamic equations for this. This does not affect this at all. It's still the case that you just add up the forces to get the mass times the derivative of velocity. Instead, what this is this tells you how to select acceptable force laws. If you do not have a force law which obeys this, then Newtonian physics doesn't care about it. Newtonian physics doesn't want to think about it. Newtonian physics says, as far as it's concerned, that's not a legitimate force. Now, there's an additional law, which we'll call Newton's third law strong. Newton's third law, the strong form, is what guarantees conservation of angular momentum. Now, not all forces obey Newton's third law in the strong form. Newton's third law in the strong form says F of 1 on 2 equals minus F of 2 on 1. It agrees with that, but it also says if you have a particle, number 1 here, and particle number 2 here, Newton's third law in the strong form not only tells you the relative direction and magnitude of the forces, it also tells you what their overall direction must be. It tells you that the direction of the force 1 on 2 must be from particle 1 to particle 2. So it's along the line going from particle 1 to particle 2, and the force of particle 2 on particle 1 must be along the line going from particle 2 to particle 1. This is called the line of action between the two particles. This is Newton's third law in the strong form, but in general it does not apply. As I was saying, the line joining those two particles is called the line of action. And if a theory obeys Newton's third law in the strong form, that means that not only will you have an equal and opposite force for the interaction between the two particles, but you will actually notice that the direction is also determined totally based on the relative position of the two particles. Now, the last thing I want to do is examine that this law right here allows for determinism and conservation of information.